Hello everyone, welcome to the presentation on design and simulation of a 500 megawatt grid connected PV farm for Labrador, Canada. This presentation will be presented in three parts. Site selection, system sizing and scheme will be presented by myself, Syed Quadri. System analysis in SAM will be presented by Mohamad Baalbaki, and MATLAB simulations and results will be presented by Chacko. So we started with the literature review of previously installed utility scale solar power plants, and then we selected the site in Labrador province. We did equipment sizing and scheme design. We did some simulations and analysis based on varying conditions and inputs, and then we derived results and conclusions. For this study project, we have used Google Maps, PVWatts, SAM, and MATLAB. Site selection was done on various criteria such as proximity to the existing transmission grid in Labrador, solar irradiance, terrain, and proximity to the means of transport. So this is the selected plot for the project. As we can see, it is close by to the 230 kV transmission line, and it is near to the Trans Labrador Highway 500 as well as Churchill Falls Airport. The terrain of the project plot is flat, which is again underpinned by the fact that the existence of Churchill Falls Airport. Next step is to estimate the land requirement and the energy output for the project using PVWatts. So as the inputs, we had keyed in the location of the project, which is Churchill Falls Airport, Labrador, and the size of the system, which is 500 megawatts. We used fixed type PV modules. The array tilt angle was selected as the latitude angle, and the azimuth angle was 180 degree because it is in the northern hemisphere. System losses were based on the reference utility scale solar power plants. Inverter efficiency and DC to AC size ratio were taken from the inverter datasheet. So based on these inputs, the total energy generated in 1 year is 596 million units per year. Also, based on the average retail electricity rate of $0.125 per unit, the value of the energy generated will be approximately 74.6 million Canadian dollars per year. As per PVWatts, the project will require 3.33 square kilometer of land. So the next step is to size the system. In that, we first started with equipment selection. The PV module selected is Canadian Solar CS6U340M based on previous references of megawatt scale power plants in Canada. This is a 340 watt PV module. It has better efficiency in its range, which is 17.49. The operating voltage is 37.9 and the optimal operating current is 8.97 amps. For this project, we have selected the central inverter topology, in which number of PV modules are connected in series to form strings, and number of such strings are connected in parallel to give input power to the inverter. The selected inverter rating is 3200 kilowatt DC. It will supply AC power at 660 volt. The maximum input voltage it can take is 1500 volt DC. with MPPT range between 935 to 1500 volt. The power evacuation equipment for the project include pooling transformers, which will take input power from inverters, gas insulated switchgear, the grid transformers, and the interconnection line between the new power plant and the existing 230 kV transmission grid in Labrador. System sizing, calculation and scheme design. Now, based on the total number of total capacity of the plant, which is 500 megawatt, and individual PV module rating of 340 watts, the total number of PV modules required for this project is derived, which is 1.47 million modules. Now, further, based on the median of the MPPT voltage range for the inverter, which is 1217.5 volt, and the optimal operating voltage of the PV module, we have derived the number of PV modules which can be connected in series to form one string, which is 32 number of PV modules. Also, we checked if the open circuit voltage of these 32 PV modules is less than the maximum voltage allowed by the inverter, which is 1500. So our total open circuit voltage per string is 1478.4, which is okay. Now, based on the total inverter capacity of 3200 kilowatt, such 288 strings can be connected in parallel per inverter. However, inverter cannot take these many inputs, so we will have to install DC combiner boxes as the intermediate between these strings and the inverter. Plant is divided into 4 number of equally rated blocks. This is for the purpose of ease of maintenance, and also to give the redundancy in case of plant and unplanned outages. So each block has this scheme diagram. Each block will export the power through one grid transformer at 230 kV level to match with the existing voltage level of the existing transmission grid of Labrador. As shown on the previous slide, individual DC combiner box will take input from 12 number of PV module strings. Now, as per ABB's data sheet, the inverter can take only 24 number of DC inputs. So we have connected 24 number of DC combiner boxes to each inverter, and then such 2 inverters will feed power to one pooling transformer. This is a 3-winding transformer which will step up power from 660 volt AC to 35 kV. Such 20 number of pooling transformers will have to be connected to 135 kV GIS. We have selected gas insulated switchgear to reduce the space requirement, because the number of incoming feeders is large, and then at power from 35 kV GIS will be collected through a grid transformer and exported at 230 kV level. So total number of pooling transformers for the plant will be 80, 20 per block. Total number of grid transformers will be 4, 1 per block, and also the 35 kV switchgear 4, 1 per block. Power will be collected through a overhead transmission line from each grid transformer, and there will be one gantry structure which will combine all 4 overhead transmission lines and form one transmission line of 4 3-phase circuits, which will then be connected to the existing transmission grid.
So, for modeling in SAM software, we selected the PV panel module Canadian Solar Max Power, but we didn't find the module in the library of the software, so we had to manually input the characteristics and features of the panel. This panel has an rated output power of 340 watts and efficiency of 17.485%. While for the inverter, we chose the APP PVS 98058 2000 kVA module, but also we didn't find it in the software library, so we had to enter its parameters manually from the datasheet of the inverter. As you can see from the right side, this is the image for the inverter section where we entered our parameters and characteristics of the inverter. This inverter has maximum AC output power of 3.136 megawatt, while it has a maximum DC input power of 3.2 megawatt. Here in this table, we summarize the system design we did in SAM software, where the number of inverters we used was 250 and the nameplate DC capacity was 499,935.989 kilowatt, and the total AC capacity was 784,000 kilowatt, and the total inverter DC capacity was 800,000 kilowatt, and the number of solar panel modules we used was 1,470,560 solar panels, while the number of strings in this design was 45,955. And the total area that this system requires is 2,859,239.91 square meters, which is a large area. For the output of the simulation we did in SAM software, we got the monthly energy output in both DC and AC. Here on the left side, we can see the plot of the monthly DC energy output in megawatt hour per month, where the highest output was in April with 82.47 megawatt hour, and the lowest was in December with 30.84 megawatt hour. Now for the monthly AC energy output, on the right side, the highest was in April as well with 69.62 megawatt hour, and the lowest was in December as well with 22.34 megawatt hour.
The objective of the dynamic simulation is to simulate PV array output with maximum power point tracking and plot output power, voltage, and current characteristics on a time scale. The connected PV capacity is 3,133 kilowatts. Also, since the power output from the PV arrays is DC, it needs to be converted and filtered to get 60 Hz AC for the purpose of exporting to the grid. In this simulation, which runs for 2.5 seconds, the solar irradiance varies between 600 to 250 watts per meter square. These graphs show the output voltage, current, and power at the 35 kV side of the pooling transformer. You'll notice how the power output drops at around 0.7 seconds with the fall in input solar irradiance and then rises again. Toward the end of the 2.5 second simulation, the power exported on the 35 kV side of the pooling transformer is stabilized at 1,945 kilowatts. Our next objective was to ensure the control of the system. In this first case, the case load is split into two equal blocks, as shown below, each of 15 megawatts, 1 megawars. One of the loads is switched off at 1 second by opening the circuit breaker. The simulation is run for 2.5 seconds while keeping input solar irradiance and temperature constant. It is observed that 50% loss of load does not affect load sharing by the PV. However, the current profile measured at the swing bus side drops to half the value. Since the rated capacity of the PV system and the grid transformer are much weaker than the swing bus, the majority of the load current is supplied by the swing bus. Also, even during loss of 50% of the load, the voltage of the transmission line is held stable by the swing bus at close to nominal capacity of 235 kV face-to-face. Next, the output filter capacitance of the inverter is reduced to 0.15 megawars from the normal value of 0.35 megawars. Since no major excursions were observed from normal voltage and current values, a protection system is not required to operate in reduced capacitance of the inverter filter. However, reduced capacitance may give rise to current harmonics. Next, we investigate a grid islanding scenario. Here the grid is disconnected as a result of some major disturbances on the grid or an expected opening of the connecting circuit breaker. To simulate this case, the circuit breaker on the 35 kV side of the pooling transformer is opened at 1 second. This results in isolation of the grid while the PV system is still generating power. Observe that at the instant the grid is lost, the PV system current output goes down to 0 while the voltage output rises suddenly, resulting in overvoltage values as high as 235 kV on the 35 kV rated secondary of the pooling transformer. Grid islanding poses a major overvoltage abnormality for the system. To avoid this scenario, fast-acting anti-islanding protection is necessary. Protection relays in the PV system side should get inputs from the transmission line voltage and current transformer to monitor the health of the grid. At the moment a loss of grid or grid fault occurs, the protection system should act instantaneously to shut down the PV generation, thereby safeguarding the system from major installation failures. Now we'll discuss the feasibility of this system. In Canada, the average installation cost for a PV farm is $1.25 per watt. For this 500 megawatt system, the installation cost would be approximately $625 million for the additional operational and maintenance costs over the system's lifespan. The land area requirement for this system, which is nearly 3 square kilometers, is quite large. It is our observation that utility-scale PV plants are more practical in provinces with higher average solar irradiances like Ontario and Alberta. Future technological improvements in PV cell efficiency could make this installation more practical. In Newfoundland and Labrador, other renewable energy sources such as wind and existing hydro installations are more practical in terms of energy generation and net present cost. Our future work in the system would include 1. Tune inverter output filters to reduce harmonic effects in output voltage and current. 2. Perform a detailed sizing of other equipment such as DC, AC cables, transmission lines, and plant layout design. And 3. Perform a detailed cost analysis of the solar power plant. Hope you enjoyed this presentation from us. Thank you.